Hello, and after an extremely lengthy gap, I'm very pleased finally to welcome you to the 9th lecture in my series on understanding science. This is the first of 6 new lectures primarily aimed at investigating the ideas and misunderstandings commonly found in pseudoscience and conspiracy theories. Thanks so much to those of you who have subscribed so far, and to those who've written to me to thank me and make suggestions after the first set of lectures. I can only profusely apologise for the gap between the last lecture of the first set, Lecture 8, and this new lecture. This is, of course, entirely my fault, and I've been very busy on other projects, which I may be able to reveal more about in a later lecture in this series. Anyway, I hope you find these new lectures interesting, and if you do, then please spread the word on your social media of choice. The more people who can learn a bit about science, the better the world will be. At least that's my working hypothesis. This lecture is on the topic of science and scientists. More specifically, I want to talk about the difference between science, as it exists on paper, in theory, as a method for searching out facts and relationships between items in the natural world, and science, as it is commonly practised, in subjects like physics and chemistry, by fallible humans, in science departments in universities and research divisions of multinational companies. The difference between these two ways of seeing the scientific endeavour is often used and abused by pseudoscientists in order to support their case. But is it really true that science is fundamentally flawed and it can't handle the inevitable imperfection of human beings? Let's take a look. After such a long gap, I think it would be a good idea to go over some of the most important ideas that I covered in the first 8 lectures in this series. After all, I'm going to continue building on those same ideas in these next 6 lectures, so it's worth making sure that you're all up to speed at the start. First and foremost, I want to emphasise here that science is a process. I know you learned in school that science was a long list of facts and formulae, but that's really not the case. Other people might dispute my definitions here, but I really want to clarify this point because it's so important. Science is a set of ideas, methods, and processes that one can use to find out facts about the universe. It is one of many such methods, but it's the best one we have because the other methods, like guessing or relying on dogma, are all fatally flawed. Science, at least in theory, consists of the processes you have to follow to make sure that errors and misinformation are minimised as much as possible. The topic of this lecture is it possible for human beings to implement these ideas well? Of course, I argue that it is undeniably possible, and we're doing it right now. Secondly, I want to emphasise that science uses 2 different techniques for finding out about the world. Firstly, analytical methods, such as mathematics or deductive logic, start with a set of knowledge and apply rigorous rules to that knowledge to deduce new relationships. For example, once you know the law of gravity, you can follow mathematical arguments to deduce the shape that orbits should take. Similarly, Einstein's theory of relativity flowed logically from his 2 postulates without the need to gather any more information. Science also uses empirical methods and relies on inductive reasoning. By this I mean the gathering of evidence and the attempt to take the gathered evidence and use it to support more general statements about the way the world works. For example, Darwin's discovery of the process of evolution, or pretty much all of observational astronomy. The third idea that I want to reinforce is my concept of the spectrum of certainty. If you remember, all claims can be placed on the spectrum, which ranges from certainly false at one end to certainly true at the other. The zone of full certainty is really only reserved for analytical proofs. We can be absolutely certain that Pythagoras' theorem is true, for example, or that the square root of 2 cannot be written as a ratio of any 2 whole numbers. But we can't be absolutely certain about anything that was derived using empirical inductive reasoning. We have no proof, for example, that the sun will rise tomorrow, though it seems likely that it will. That sort of claim would be positioned arbitrarily close to the certainly true end of the spectrum, whereas the claim that the moons of Jupiter are in fact made of cheese would lie arbitrarily close to the certainly false end. Science consists in one thing only, attempting to move every single claim about the universe as close as possible to one or other end of that scale. That's all it is. How do we accomplish that? Well, that's the realm of Bayes' theorem and the scientific method. Bayes' theorem, if you recall, is the rule that tells us how to add evidence together. So we can take a claim that lies at any point on the spectrum of certainty and see what happens to its location on the spectrum when we add in some new information. And all of this takes place within the umbrella of the scientific method, which is traditionally stated as a sort of flowchart that tells us how to investigate the universe in the most reliable way possible. Develop hypotheses about how the universe works, test them, then, based on the evidence of your test, accept, reject, or modify those hypotheses. Maybe go out and find more data, shifting our hypothesis towards one end or the other end of the spectrum, wherever the data lead us, until we're satisfied. Then, perhaps most importantly, continue to revise and improve your ideas as more information arrives. Finally, I just wanted to remind you of the topic of these next 6 lectures, at least loosely, and that is pseudoscience. A pseudoscience is something that pretends to be a science, but isn't. Some pseudosciences are hoaxes, like dodgy medical scams, for example, whereas others are just the result of often well-meaning but ultimately ignorant people attempting to push ideas that are scientifically nonsensical, like homeopathy or psychic powers. Right, that's enough for the recap. Let's learn some new stuff. What does it mean to be a scientist? Well, in the common usage, a scientist is a person who uses science prominently in their job. So a chemist, a physicist, a geologist, those all count. And of course there are very many more. And I think that's pretty much the standard image of a scientist that most people would conjure up if asked to describe what the term means. But in that sense, I don't see being a scientist as different to any other job. Science is just a skill to be learned, just like, say, being a programmer or a carpenter. Being good at science means a lot more than memorising a load of formulae. It requires that you master a specific way of thinking and behaving that conforms to the scientific method as closely as possible. And different people have different levels of skill at science. Some don't know how it works at all, and others, like you if you've been listening to all my lectures, will be beginning to develop a pretty good working knowledge. But science is more than just knowing how to behave. It's also about developing the methods of thought that lead someone to adhere to the scientific method as closely as possible. I could teach you the names of all the keys on a piano keyboard, for example, and show how they map to the dots on manuscript paper, but that doesn't mean that you can play the piano. Science has a lot of knowledge associated with it, but also learned skills that you have to practice to get good at. So I think it's fair to say that you don't have to make money from a scientific discipline to be a scientist, just like you don't have to make money from playing music to be a musician. And to say that being good at science involves understanding quantum mechanics or chemistry is just as wrong as claiming that being good at music implies that you must be a concert pianist. There are plenty of musicians who can't play the piano at all, and in fact there are truly world-class musicians who, through infirmity or disability, cannot play any instruments whatsoever anymore. Does that make them no longer musicians? Of course not. So just to be clear here, science is the process that is followed by scientists. And we, as a species, have applied science to a wide range of topics and built up a huge amount of knowledge using it. If you want to be a quantum physicist, say, then you better learn all the maths and formulae behind quantum physics. But that's just one branch of science. Just like if you want to be a professional clarinetist, you better learn to play the clarinet. But that doesn't mean you're a terrible musician if you can't play the clarinet. I guess it's possible to be really good at applying the scientific method to derive new information, but never actually applying yourself to learn what other people have already discovered using that method. I don't know why you'd want to, but you could. I worry about generations of children who think that they don't get science, or that they're terrible at it, just because they couldn't do the maths behind Newtonian dynamics, or they couldn't remember the chemical formula for methane. But that's confusing the process of science with the discoveries made using that process. It's perfectly possible that they were very good scientists all along. If that story rings true for you, then I hope you'll think about whether the conclusion might also apply to you. When we think of science as a discipline, we automatically think of large laboratories, university lecture theatres, perhaps large-scale projects like a major astronomical observatory or the Large Hadron Collider. But it certainly hasn't always been like this. After all, the word science was only first coined in the 19th century. As we begin the 19th century, large amounts of research was done by the gentleman scientist, and of course it was almost exclusively rich men who did this, though there are a few notable exceptions, of course. It was still possible for one person to be a natural philosopher who knew pretty much everything about most of the scientific discoveries that had been made to that point. But during the 19th century, science got much more complex. Chemistry was beginning. Atomic theory had entered the scene. We had electromagnetism, evolution, the discovery of radio and telecommunication. And it was only a few years into the 20th century when Einstein published his first papers on relativity and quantum theory. The sum total of scientific discoveries was getting much larger than it had ever been before, and much more complicated. Now it took years to get up to speed with just one topic, and science was becoming increasingly lucrative too. No longer seen as the pastime of noblemen with too much spare time, the prospect of rapid global communication, flight, the automobile, electricity, it all catalysed the birth of a new profession, the professional scientist. At this stage, thanks to the now mature technology of printing, scientific journals began to take off. They had existed in a very limited form since the time of Newton, but now they were available to the mass market at a fraction of the cost. This formalised exchange of knowledge, together with the now vastly more complex theories and experiments that scientific progress required, all worked together to build what has become known as the scientific establishment. Of course, this continued with the 20th century. Science, as a specific topic in schools, was only really introduced in the last 100 years, and national governmental bodies to oversee scientific research started cropping up around the time of the First World War in the UK, and then a few decades later across the developed world. Because the education was now in place, more and more people started working in science as a profession, and scientific discovery flourished. Formal peer review, something that we would now consider of vital importance for the integrity of the scientific process, only really began in the 1960s. I mean, people did scrutinise publications before then, but the formal process itself is remarkably recent. Finally, in the last few decades, we have really started to see mass collaboration on enormous, large-scale works. You could possibly argue that this began with the Manhattan Project and the race to build the first atomic bomb. But it certainly continues today with the Hubble Space Telescope and the Large Hadron Collider. These are machines that cost many billions of dollars to build and operate, and could only be undertaken by wealthy governments. The age of the individual scientist is well and truly over. That's not to say that individual amateurs don't contribute to science. There are many crowdsourcing efforts that prove otherwise. But the giant steps forward are now much more labour-intensive, expensive, long-term processes, conducted by dozens or hundreds of independent researchers over decades. We have come from Newton peering at sunlight through glass prisms in his Cambridge study, all the way to multi-decade, multi-billion-dollar, continent-spanning research efforts investigating topics that nobody but a tiny group of experts has any hope of understanding. And of course, when you set up any large organisation, it always has its flaws. Let's take a look at some of those next. So, science is a process, and it's implemented by humans. And inevitably when that happens, some things go wrong. Of course they do. Human beings make mistakes. We have our own personality flaws. We're often too keen to believe things that seem comfortable or convenient, and too keen to reject anything that goes against what we already believe. The fact that science is implemented by human beings obviously leads to some inevitable mistakes. It's well known now that Isaac Newton, probably the greatest scientist who ever lived and the father of modern physics, was also into alchemy. He spent many years of his life investigating whether he could transmute substances into other substances, or make magical potions that bestowed immortality. It seems quite strange, now we think of it, to imagine someone so prominent in the history of science being taken in by such a bizarre delusion. But it's also worth noting that it wasn't anywhere near so strange at the time. In Newton's day, elements were not understood. We didn't have atomic theory, we didn't know about protons and electrons and neutrons. For Newton, the claim that he could turn lead into gold was actually not that extraordinary. But nonetheless, despite many decades of failure in this investigation, he persisted in his search to no avail. For a more modern example, we could use Albert Einstein, who is known today as the father of relativity, but also laid much of the groundwork for quantum theory with his paper on the photoelectric effect. However, later in life he decided he didn't much care for the direction that quantum physics was taking, and spent much effort trying to denounce it, with zero success. Nowadays, quantum physics has flourished into a wide range of specialised subdisciplines, and Einstein's negativity towards the subject proved entirely ill-formed. Finally, what about Fred Hoyle? The famous cosmologist coined the term Big Bang as a joke to poke fun at the notion that the universe might have begun with an explosion. He spent much of his life denying Big Bang theory and insisting that the universe has been maintained in a steady state for eternity, with matter being created spontaneously at the centre. Quite why he thought that was a more plausible model is unclear to me, but he continued to defend it well past the point where it was obviously wrong and Big Bang Theory was obviously victorious. Hoyle also opposed evolution, at least in its fullest sense, not believing that it was possible that life on Earth today, in all its forms, came from such a simple process. Again, science had proved him wrong, and he refused to change his mind. Sometimes, however, errors creep into the scientific literature not through honest misunderstanding, ignorance or reticence, but instead because of dishonest or even criminal deception. The most famous recent example of this is probably the case of Andrew Wakefield, the former doctor who was struck off the medical register in the UK after being convicted of fraud and unethical behaviour. The principal reason for this action was his 1998 paper alleging a link between the measles, mumps, rubella or MMR vaccine and autism in young children, a paper which has since been fully retracted by the Lancet journal in which it was published. You know someone is bad news when they have a section all to themselves on the Wikipedia page for scientific misconduct. It turned out that Wakefield had basically lied and carried out unnecessary and invasive medical procedures on children without ethical approval. He'd falsified data, he'd aimed to profit by doing so by launching a venture on the back of his fraudulent study selling diagnostic kits for the non-existent medical condition that he made up as part of the 1998 study. He was convicted of serious professional misconduct in January 2010, after which he fled to the United States, where he still scares parents with lies about vaccines, and is partly indirectly responsible for the return of vaccine-preventable diseases in several parts of the US, outbreaks which have already caused a great deal of suffering, and have unfortunately now cost lives. Oh, and Wakefield received over £435,000 from the Legal Services Commission before his study in order to build a case against the MMR vaccine. This was 2 years before the Lancet article was published. Pseudoscientists and conspiracy theorists often suggest that scientists deny these delusions because the scientists are somehow in the pocket of big business. But in reality, the reverse is often true, as it was in the case of Wakefield. And in 2012, the Cochrane Library, an organisation known for conducting extremely thorough meta-analyses looking at multiple studies in a statistically solid manner, published their examination of the MMR vaccine, where they studied 14,700,000 children, in comparison to Wakefield's 5, and concluded that there was no credible evidence of any involvement whatsoever of MMR in autism. A June 2014 meta-analysis concluded the same for childhood vaccinations of all kinds from a total sample of 1.25 million children, and in July 2014 published another study showing that MMR was not linked with childhood autism in any way at all. Another famous scientific miscreant was Japanese anesthesiology researcher Yoshitaka Fujii, who probably holds the rather ignominious record for the largest number of papers containing forged data ever written by one researcher, at least as far as we know. The tally stands at no fewer than 172 papers, and possibly even more. Largely this was in his work on countering nausea and vomiting after surgery. When other scientists attempted to replicate his findings, they discovered that Fujii's results did not match up with their own discoveries. The results were also suspiciously uniform. Eventually, the full scale of his deception became known. He was dismissed from his post in 2012, and the papers found to be fraudulent have all been retracted since. Why exactly have I just spent several minutes giving examples about prominent scientists who got things wrong? Well, partly because I want to investigate how science is self-correcting, which I'll talk about in a few minutes, but also because it's important to realise that all these controversies, big and small, actually have a grave cost on the credibility and effectiveness of the scientific establishment. And it's a cost that affects everyone. Moreover, it's a cost that really shouldn't exist, because science as a process isn't in question here, just imperfect human beings getting things wrong. The most obvious implication is mistrust. If scientists get things wrong, then the public will trust them less in future. And the public mistrusts scientific research in a wide range of areas, from genetic modification of our various foodstuffs to nuclear power, and a wide range of health and dietary advice. The common thread is usually along the lines of, well, scientists have got things wrong before, so why won't that happen again? The situations are, of course, completely impossible to compare, but that doesn't stop the anti-scientists from pursuing their agenda. Another implication is disengagement of the general population from scientific subjects. We see that today in many Western countries with a lack of science, technology, engineering and mathematics graduates coming out of higher education, and that obviously has profound economic implications for those countries. If science is not seen as a highly valuable skill, then we shouldn't be too surprised that our young people are not inclined to pursue it. Finally, dishonesty and errors in scientists often lead to, or at least fuel, denialism. That is, the denial of extremely well-established scientific facts by large swathes of the general population, based usually on misinformation and irrational emotional responses to topics that are poorly understood by those opposing them. I've already mentioned a few topics that often suffer from this symptom: genetic modification, nuclear power, medical advice, but there are many more. The most high-profile cases these days are probably global warming, evolution, vaccination. In all three cases, the scientific consensus is absolutely overwhelming, essentially unanimous and undeniable. But in all three cases, denialists manage to convince themselves that the scientific community has it all wrong, and that their own particular view is the truth. Sometimes this happens because dishonest or fraudulent research is used to back invalid pseudoscientific claims, like in the case of the anti-vaccination movement spurred on by the inaccurate, unethical and misleading research of Andrew Wakefield that we saw on the previous slide. But sometimes the link is more subtle. Creationists, for example, are fond of pointing out the times that fossil hunters have been fooled by fake fossils, or have misattributed some creature in the wrong genus or species. The creationists' argument presumably being that every single one of the millions of other fossils so far collected and categorised is also somehow wrongly identified to the same degree. So that's more than enough about how things go wrong. What can we actually do about it? I mean, it sounded pretty bleak so far, but none of this is a problem if we have a way of dealing with these issues, right? So let's take a step back and look at the situation we find ourselves in right now. Science is an ideal, a process that we would like to implement, but ultimately, being human, we don't quite implement it perfectly. We do what we can, and science itself is designed precisely to minimise the possible sources of error, for example, by designing experiments meticulously, or by carrying out data analysis in a rigorous and consistent way. But sometimes mistakes occur. So here's the most important point on this slide, perhaps in the entire presentation. Science does not dictate dogmatic truths. It simply follows the evidence and logic. So, if the evidence changes, then the scientific consensus should change. It seems to me that the most absolutely vital aspect of any system of understanding, or of any method for discovering how the universe really works, is that it must be mutable. You must be able to change it if we discover that we got things wrong. Science is designed to be exactly like this. There is no scientific claim that cannot be examined, and there is no theory or law that can't be overturned given sufficient evidence against it. Now, in some cases, it's extremely difficult to imagine even how that evidence might come about, but in theory, it's always a possibility. I'm not sure what evidence I could possibly find to convince me that the theory of gravity was false, for example, given that it so beautifully describes so many things and has always done so since Newton first described it. I mean, Einstein modified it a bit in some extreme cases, but in general the Newtonian laws are pretty solid. But if some evidence were to come along and prove that gravity were actually wrong, that when we think planets are orbiting due to gravity we're actually deluded, then the law of gravity would of course have to change. That's the bottom line. There are no sacred cows, no theories that are absolutely beyond question. Of course, if you ask a scientist where it's worth putting your effort, or money, then there are certain lines of inquiry that they will strongly oppose. It's simply a waste of time spending government money investigating psychic communication or homeopathy, for example, because they're so utterly impossible and no convincing evidence has ever been gathered to convince anyone otherwise, despite many people trying. If you like, they're right next to the absolutely provably false part of the spectrum of certainty. There's no point throwing away more money at the problem, it's pretty much decided. But if you want to spend your own time and money trying to overturn bedrock theories of science, then go ahead, knock yourself out. If you succeed, then fame and fortune await. Science thrives on that, instead of forbidding it. Scientific establishments usually forbid it because they have a fixed budget and it needs to be spent where it's most likely to have a positive result, but that's another question. The second thing about science which makes it great at resisting the sort of issues that we've discussed in this presentation so far is that it's self-correcting. By this I mean that the actual process of science has built-in safeguards to ensure that every new finding is scrutinised as closely as possible. For a start, scientists are a varied bunch, and there's a lot of them. Not only does this maximise the chance of new discoveries being made, because the more diverse the minds you throw at a problem, the more likely you are to find novelty, but also the fact that there are many minds means that any mistake in a published work is more likely to be spotted, because someone might think of a test or an alternative explanation that the original authors missed. Science also encourages the sharing of results by peer review and open publishing. Scientists' careers are often built on healthy publication records. The more they share, the more their career progresses. And, of course, the more information is shared, the less likely it is that false conclusions will prosper. After all, it's very much harder to get a lot of people to believe in your wacky theory if there are already 100 papers published in reputable journals saying exactly the opposite. Finally, scientists are incentivized to find and to correct errors. If you can prove an established theory wrong, then your academic career, your fame, and maybe even a Nobel Prize is assured. And whenever anyone publishes a paper contradicting your pet theory, then of course you'll spend all your efforts attempting to find holes in that paper's methods. This way, new theories are subjected to intense scrutiny from highly incentivized experts at every opportunity. And the more remarkable the theory, the more remarkable the claims, the more intense that scrutiny will be. This makes it as difficult as possible for erroneous theories to continue unquestioned. I've shown that science is self-correcting, but we can and should also be attempting to prevent false studies and mistaken conclusions from ever being published in the first place. How do we do this? The answer is, of course, the process of peer review. Now, I've talked about this already in several other presentations, so I won't go through the process itself, but it's probably accurate to say that peer review is very much like a built-in immune system that science has developed in order to identify and remove falsehoods before they get a foothold in the scientific literature. Peer review isn't just there to root out frauds, charlatans and lunatics. It serves a very important function in checking the work of honest, motivated experts to make sure that they've made a watertight case for their conclusions. After all, besides fraud, experiments could be wrong because the experimenter actually brought some biases into the experiment, and those influenced the answer unfairly. Alternatively, the person analysing the data might have made a mistake in their analysis, or maybe the experimenter was just ignorant of an obscure finding that shed doubt on their conclusions. Either way, papers are often flawed when they're first written, so the process of peer review aims to iron out the creases and see if there's a solid case left underneath. Sometimes after peer review the paper is withdrawn completely, or at least very heavily reworked, in order to answer specific faults in the experimental method. Of course, peer review itself isn't perfect. The reviewers can fall prey to the very same human weaknesses that affect the original authors. Maybe they suffer biases, maybe they're also ignorant of key facts. They might be frauds, they might do a poor and half-hearted job. After all, even young Earth creationists have their own peer-reviewed journals in which they publish their crazy theories, but of course nobody takes them seriously because they're extremely careful to make sure that the peers who do the reviewing are all suffering from exactly the same stubborn lack of comprehension, powerful underlying biases and blindly motivated reasoning that the creationists themselves maintain. Peer review only works if your peers aren't willfully ignorant. But it's definitely a good start. So far I've concentrated on what happens when a scientist gets something wrong, deliberately or not. But what about ideas that were perhaps seen as plausible for a long time, but which gradually found the evidence going against them, yet still a stubborn group of defenders rallied around and continued to defend their theories long after they were still plausible? What about entire teams of scientists who followed dead ends and falsehoods en masse, refusing to deviate from their beliefs and disrespecting those who disagreed with them? Max Planck, the famous physicist partially responsible for the birth of quantum theory, said, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it." And of course there's some truth to this. We can all list names of stubborn scientists who refuse to change their minds. Fred Hoyle, of course, who we mentioned earlier. There are many more, but equally there are many examples of scientists who did change their mind. It's just that someone changing their mind isn't nearly such a big story and doesn't stick in the memory as much as one lone maverick boldly denying the entire scientific establishment, so we tend not to remember it. After all, Charles Darwin set off on his famous journey on the HMS Beagle fully convinced of the religious theory of creationism, and later changed his mind both on religion and on the creationist theory, in a big way. Stephen Hawking famously changed his mind recently about the ability of information to leak out of black holes, which led to him conceding a bet that he'd previously made with the theoretical physicist John Preskill. And then there's Bill Nye, the science guy from the popular television series, who recently admitted that, after being initially sceptical about the safety of genetically modified organisms for human consumption, he now believes that they are indeed safe, and also extremely promising for solving a whole host of different human problems related to nutrition and farming. In other words, he's come into agreement with the scientific consensus. So there's ample proof that scientists, even high-profile ones with big egos and loads to lose by admitting they were wrong, do change their mind, even about big issues, and on a regular basis. But let's go further. Let's imagine that we were inventing a process that was tasked with finding out complicated and often emotionally charged information about the universe, and we wanted to make it as immune as possible to this problem. What would we do? Well, first of all, we would make sure that no facts were sacred. Everything should be open to challenge, no matter how fundamental it is to the current consensus. If Newtonian physics had remained untouchable, then relativity and quantum theory would probably never have gotten off the ground. Secondly, you should incentivize contrariness. As I explained a few slides ago, science does this by offering big rewards to those who overturn established theories. If there are 1,000 people all publishing papers on the consensus, then it's very difficult to make a mark. But if you can publish something solid and in contradiction to that consensus, then you stand out a mile. And if the consensus then swings in your direction, then you'll find yourself at the head of a new scientific theory, and your name will be attached to the discoveries. That's a huge incentive. Thirdly, you should always insist on objective evidence. That is, evidence that is much harder to fake, lie about, or misremember. You should make your studies properly blinded wherever appropriate so that your biases don't influence the result. You should get independent analysts to reduce the data, also blinded, to further avoid biases creeping in. You should always avoid any unreliable sources of information that could easily prop up falsehoods, things like anecdotes, opinion and hearsay. None of these has any place in science for exactly this reason. Lastly, ideas should stand on their own merits. That is to say, it shouldn't matter who suggested a theory or how many people back them up. Ideas should be judged on the merits of the theoretical and experimental backing that they come with, and nothing else. In short, if you were looking to produce a process that was as resistant as possible to groupthink and delusion, you would create science. And, as it happens, that's exactly what we did. So, in summary, I want to emphasise a few fairly simple points. Firstly, science is a set of methods. We can all follow scientific methods, even if it's not our actual day job, and many of us do exactly that. Every time you hear an unusual rumour and think to yourself, that doesn't sound plausible based on what I already know, I wonder what kind of evidence I would need to believe that. You're actually doing science, and probably subconsciously you're invoking Bayes' theorem. Similarly, if you've ever thought, I wonder how that works, when taking something apart, you're doing science. If you've ever conducted a survey or experimented with the settings on your microwave oven to see how best to cook vegetables, you're doing science. But science is definitely a skill. You can be better or worse at it. You can get it wrong, and people often do, even professionals. The process of science must necessarily be implemented by human beings, so mistakes are made. People get things wrong accidentally. They introduce subconscious bias into their analysis. They make mistakes, but they also deliberately lie and cheat. Some people are swayed too much by emotion and refuse to accept otherwise overwhelming evidence. And still others lack the courage to stick with unpopular theories, even if they're right, because they feel the pressure of holding a contrary opinion. None of this should be news to you, and none of it is remotely surprising. And moreover, none of it matters, because science doesn't need to be implemented perfectly in order to produce great results. But even better than that, science also comes with built-in mechanisms to protect itself from error as thoroughly and effectively as possible. It insists on excellent evidence, avoiding misleading and potentially biased sources of information. It is self-criticising, with peer review and replication acting like an immune system to keep out error. It's open to change. Any theory can be challenged if you can gather sufficient evidence to make your case. There is no such thing as a sacred truth in science. And finally, science is self-correcting, meaning that scientific theories are always being reviewed, revised, adjusted or reinforced wherever necessary, as new generations apply their own curiosity to established findings. There have been a number of highly complex philosophical attacks made on the process of science, particularly in the 20th century. I would say that science has proved, by its continuing success, that it is the best tool we have to investigate the world around us, and that it demonstrates that by continually improving the world in which we live. That's the end of this lecture. I hope you found it useful. If you think these lectures are worth watching, then please spread the word and get them out to as many people as possible. I'm hoping to release another one in maybe a few weeks' time, so do subscribe to get the latest notifications. And if you have any suggestions for new videos, please let me know. Next time I'll be talking about the supernatural. What's it all about? And how does science approach supernatural claims? Thanks very much for listening.